We're just going to give it a couple more minutes before we get started, give people a chance to get seated and everything. But hope you share your table if you still got some open seats. It's like a pretty good turnout tonight.
Make a hole.
Just settle.
How many square? And one left.
Okay, well, without further ado, good evening, everyone. I'd like to thank everyone for coming and welcome to our panel on the future of nuclear energy. We've got several members of the Idaho National Laboratory leadership and representatives of our research organizations here tonight to talk about different aspects of the work that we have going on at the lab right now. My name is Joe Campbell. I'm a communications specialist for the Advanced Test Reactor. That's our flagship irradiation facility out of the lab. But I don't want to get distracted talking about my favorite topic, the diamond in the desert, as I like to call it. So let me stay on track here. Now this is an interactive format. It's something we've tried out a couple of times with some of these panel discussions that we've had in the past. So you all drive the direction of the discussion. We're going to put a selection of the questions that we've gotten on this topic area, or each of the 4 topic areas, I'm sorry. And you'll be able to vote on them and you'll see the results in real time. And so you're sharing the discussion. And then we have been taking questions over email, and we're going to get to many of those as we can. And then, of course, we'll try and save some time at the end to answer any questions that you have on these topic areas as we go. So if you'll see a QR code for the panelists for their biographies, so if you want to find out a little bit more about them, I'll introduce each of our panelists here. So there's more details there, and then go ahead and flip to the next slide. And this is how you get logged into the POL EB system. So you can just text that code, and it'll give you instructions for their little app. It's pretty slick. So while you're working on that, I'm going to start introducing our panelists here. I'm going to start with Lori Brazzi, and she's a business development executive supporting INL's nuclear mission organization. And we'll give her a few minutes a little bit later to go in a little bit more detail as we get started. And then Jess Guillen. Jess Guillen, sorry. I've always done that wrong. Jess is the Associate Laboratory Director for the Nuclear Science and Technology Directorate at INL. And then next we have Marianne Walk down at the end. And she is our Deputy Lab Director for Science and Technology and our Chief Research Officer. And then Stephanie Weir, and she is a Siting and Regulatory Strategy Manager for the National Reactor Innovation Center at INL. And she'll go into a little bit more detail on what that is about. So I hope everyone's had a chance to get logged in on the POL system. To kind of set the stage, nuclear energy is becoming a very big topic lately. And there's a lot of good reasons for that. Nuclear power plants, don't generate any carbon emissions while they're generating electricity. There are about 426 reactors, according to the latest statistics from the International Energy Association, currently operating around the world, and that makes up about 10% of the global energy supply. Here in the U.S., we have 92 commercial plants still operating, and they provide about 19% of our total energy supply in the U.S. and just over half of our low carbon energy. That's pretty impressive, but every projection of population is showing that that's going to continue to grow. The energy demand is going to grow, and if we don't have forms of energy that can do that with minimal carbon emissions, that doesn't help any of our goals for carbon reduction, that we've signed up for. There are 2 commercial plants under construction in Georgia right now, and then there's a lot of attention right now on new types of reactors, micro and small modular reactors in particular. And INL, of course, has a very big role in that. Now, we always start these discussions off with the word cloud, and we'll ask a very simple question. Everybody's already started there. And we'll do the same question again after the discussion, just to see, for interest's sake, how much has changed based on what you may have learned from our panelists here tonight. So I've already done a quick intro. So let's go ahead and get to our first topic area, and that's the partnerships with public and private industry. And that's Lori Brazzi's area of expertise. Now, while you're voting on the questions that we have on the screen, Lori's going to introduce that topic a little bit. Go ahead. Yep.
Sorry, I have to get up and walk around. I'm not good at sitting down. Okay, so while you're voting on those, I am a business development executive at the INL, and it's relatively a new position for me, but I've been doing work with programs and industry for 33 years now. So INL has been involved with different forms of industry and other national labs, and it is an exciting time right now to be in the lab and to be working with industry, and it's like an anthill. People are coming out all over wanting to know more about nuclear and more about how the labs can help, and so we're very busy. We've been asked a tour group. They're giving tours daily out there. So it's very exciting. It's a fun way now to end my career as I get older and get ready to retire shortly. But we do a lot of work with industry, and that industry is nuclear developers, small modular reactor developers, micro reactor developers. The supply chain is a big deal. We are working with different suppliers to get them into the labs and get them working with our test beds and get them working with our scientists and engineers. We're developing new inventions all the time. We've got investors that are interested in pouring money into these developers right now. And we have new developers coming out. They're not just the same developers we've had all along. Every year we've got 3 or 4 contacting us that are newly developed, newly invested in. So that's my intro, Joe.
All right, thank you.
But I need the next slide.
What's that?
That's what I really want to talk to.
Okay, well,
So,
let's back up one and
Oh,
look at the question. That
okay.
Okay, so what kind
Okay,
of projects are attracting investors right now?
So
What
let's,
do we do if we're banned from the poll? How do we fix that? Undo?
What was that?
We get banned from the poll, we hit undo, does that work? You're back in the poll?
Abandon the polls.
you're banned from the poll.
Well, allegedly.
Uh-oh.
Can't
I don't even know what to do that.
Send a clear answer. Okay.
Can somebody help with his polling?
Call me Hermes.
Okay, so this is a really great slide. Just really quickly, it will give you an idea of some of the projects that are going on. Project Pele, Marvel is our little micro reactor that INL is developing. Project Pele is a Department of Defense reactor. Dome is a test bed at INL. It is the old EBR-1 dome that they have emptied out, and we're going to put some microreactor demonstrations in that dome. The Lotus test bed is a test bed for TerraPower. They're going to do multiple experiments in this test bed, and I'm using a lot of acronyms right now, but I can tell you what those are in a minute. McCree is the TerraPower experiment. Lotus is another test bed at the INL. Kairos is not demonstrating at the INL, but they plan to be online by 2026 to demonstrate. X Energy is also not demonstrating at INL, but they've got a 2027 date. Oklo is another developer. They are planning to demonstrate at INL. UAMPS, you've heard about NuScale. They are looking at a 2029 date. The VTR is a concept reactor that we are working on, not actively right now. It's been put on hold, but that would be a test reactor at the INL at some point. And we've got Holtec, SMR, and Natrium, the TerraPower reactor. So it's just kind of a nice timeline. These dates have been provided by the developers, so they're not our dates, but other than INL dates. Okay, that's it.
Yeah, and you can also back each other up on the panel if you want to make another point that the panelists covered and add some additional information. Feel free to do that.
Did I answer the question?
You did. That
Oh.
That covered quite a few of the projects.
Okay. These are just a few of the projects. We've got many more.
Yep. And are there any follow-up questions for the audience about any of those particular projects?
Just one quick one. Can you describe the different chemistries of the different types? For example, heavy water versus sodium versus gas-cooled, et cetera?
Yes, please.
Okay, I'll take that.
And the safety testing associated.
Okay, yeah, so I'm Jess Jean, I'm Associate Laboratory Director for Nuclear Science and Technology. So I'm responsible for a lot of the research and development on these nuclear systems. Can we go back to that timeline slide? Yeah, so there's a range of technologies on these reactors. Starting, if you look above the timeline with Marble, that reactor, the coolant technology is liquid metal. We have a lot of experiments with liquid metal. The fuel technology for that is uranium zirconium hydride fuel, which is the same fuel used in university research reactors. So this type of fuel has been used for a long time. The coolant is well known and used for a long time. There's a lot of experience. I'll try to put my lips closer with that. And it's a very low power reactor, so we understand its performance very well. As you move through these, the Project Pele gas-cooled reactor, maybe you've heard of these technologies, uses this coated particle fuel, TRISO fuel. This is fuel that was researched, developed, tested at Idaho National Laboratory. Very robust, high temperature fuel, and that reactor is cooled with gas. It'll be nominally at, say, around a megawatt class reactor, and so we'll be testing it. And then, I don't know if you want me to go through all these. I certainly can.
Just roughly the different types.
Okay.
Quick follow-up on the gas type, if we can chase that question down.
Okay.
What gas, if it's not a carbon-based gas?
Yeah, it's helium. So we use helium as an inert gas, yeah. So it doesn't interact with the materials. Yeah, so we have up here salt-cooled reactor. The Hermes is salt-cooled reactors. Salt sounds like a weird material for a coolant, but salt is like sodium chloride is an example, but there are also salts based on fluorides. And these are compound materials that can have very high heat capacity. So as you can imagine in a reactor, you'd like your coolant to be able to absorb a lot of heat. So that's a good material for that. Sodium as a coolant, we've operated a number of sodium reactors. EBR2 at the lab we've operated for quite a while until it was shut down in the 90s. So liquid metal, we call that. So it's sodium. Sodium is a good coolant because it has very high thermal conductivity, so it can also remove heat very well. Water, of course, UAMPS, NuScale is water cooled. Voyager listed there. The SMR Holtec is a water cooled reactor, very similar to our current light water reactor technology. So let's see, I think I touched on everything there. I can go deeper if you want. Just to make sure I just sort of touched on the
And
things.
I'm just hoping at some point you'll talk about the energy scale. For example, you mentioned
Oh,
megawatts
okay.
versus hundreds of kilowatts,
Yeah.
for the different sizes.
Okay.
You'll get there, I'm sure.
Yeah. So yeah. So why don't we come back to that? If we don't get to it, raise your hand, ask that question. Happy to talk about that. Okay. So ask your question and maybe one of us can answer.
Okay, really quickly, I thought that the NuScale reactor was not going to be
reactor core itself is water cooled. That water just circulated in a loop. Then what you have, so these reactors, you circulate that to cool the fuel, run that through a heat exchanger, which is within the vessel, heat, boil other water that runs a turbine, and then you're going to have to reject that heat before that secondary system goes into the reactor. So you're thinking about the secondary system, the water needed to cool the secondary system. NuScale is planning to use dry cooling, which there's a loop. So unlike some plants that do once cool, which you may take water out of a river or out of the ocean, run it through, and then put it back in. So you can imagine the throughput and the cumulative throughput of water is quite a bit of water. If you have a large lake or ocean, there's a lot of water. Dry cooling, you circulate that water, so you reuse it. There will be some makeup water that's needed, but it's I don't know if I recall the exact number, but definitely order of magnitude lower than the ones that are cooling. Okay. Joe, why don't you moderate who's...
Yeah, we'll probably better move on to the next topic, but please save your questions. We are going to take some more of these as we go, because I think we're going to hit a lot of these topic areas as we go through.
If we don't, we'll hang around.
Yeah, we'll come back to them, definitely. Okay, the next subject area, go ahead and start voting on your questions, and we're going to talk, go into a little bit more detail if we haven't covered already on the microreactors and their applications. Vote on those, and Jess, if you'd like to talk a little bit about
Microreactor. Maybe I'll talk a little bit about what we mean by microreactors and the sizes of different reactors. Our current operating reactors in the U.S., there's I think 92 reactors operating. These are large reactors that produce nominally a gigawatt, 1,000 megawatts each. So these power cities are big, provide very reliable, low-cost energy for the grid. So that's a large reactor. You can move down in scale, small modular reactors by definition, and then some people's definition varies a little bit, but these are nominally 300 megawatts, so about 1/3 the size, and they're usually composed of modules. And you think of the NuScale reactor, each module can be 50 to 77 megawatts, and you put several of these together to get up to 300, 400 megawatts. So you can scale those. So you can think of a small modular reactor as certainly smaller than the large gigawatt reactors, but also modular, add capacity as you need it. And then you get to the microreactors, which is this application. Microreactors tend to range from megawatts to 10 megawatts. They're designed to be fully factory fabricated. You can see the notional picture there on a truck. It can be transported, deployed, and then when you're done or you use up all the energy that's in the fuel, you can take the reactor back and either refurbish it or disposition it at that point. So very transportable, likely to power facilities, data centers, maybe you use these at mines, other places where you need a lot of reliable energy. So ranging from that, like an application, which is what the question will be about, we'll get into that, up to where you power cities. So the takeaway is reactors come in ranges depending upon the application that you intend to apply. Okay, so hopefully that answered sort of the question about the difference between the scale of these reactors.
Okay, and then the number one question there is, can they really make a dent in our carbon emissions?
Yeah, this is I don't know, if you want me to answer this or...
Or, yeah.
I'll take a shot at it. We have so the reason why this comes up is because, as I mentioned, they're small, right? So you think about the amount of energy we use, which is quite a bit. A single microreactor on its own, of course, will produce carbon-free or low-carbon energy and would replace diesel generators. So the local conditions is certainly very helpful. And then it depends on making a dent. If you look at the global carbon emissions, it would depend on the scale of deployment of these reactors. If they're proven to be cost-effective, fully, if you think about fabricating things in factories, we're pretty good at churning out a large number of factory-produced items. And if we get into production mode where they're at scale, then I think they actually can have a good impact and make a dent in carbon emissions. All that has to play out over time as we demonstrate them, and you saw the timeline of demonstrations. And then connect these up to the applications where they're using heat and electricity, and using them for the a growing number of data centers or ganging them together, having multiple microreactors that can then power.
And just the idea of the communities that are using oil generators in Alaska, or the mining communities that are having oil shipped in to run generators for mining, they're run by a microreactor, that oil isn't needed for that generation.
That's true.
So that kind of compounds the savings, not just the power generation itself, but also the transportation of fuel.
So there are a few questions I don't want to.
It's a double bonus. Yes, sir.
What's the service life of a microreactor?
It can vary depending on design, from maybe, on the low end, 3 to 5 years, on the high end, 20 years. And again, they will be designed to be, take the reactor back, either refuel it. It'll be a different concept of operations in our current fleet, that we fuel, the facility's fixed, you refuel it, you have options on this with microreactors.
Yes, sir.
The small modulars I've seen are, when they are intended to be used for generating electricity, some suggestions was we're looking at 8 to 10 to 12 cents a kilowatt hour. For these micros where there's a locational benefit, I would assume it would be a higher price per kilowatt hour or megawatt hour. Can you give me an estimate of where you think that might clear when the technology is a little more mature?
I'll get this. It will vary again on size. Smaller reactors are going to have a higher cost, levelized cost of electricity. That could be, 40 cents. You look at some of the applications in remote areas, there's definitely a market for that. It's going to be hard in a small reactor to get this down to a few cents per kilowatt hour. So you're really looking at those specialized applications that can benefit. Either they're remote, they're paying very expensive cost to truck in diesel, or there's a reliability need that you're willing to pay the cost for that. There's also benefit, I'll just close this up. There's also benefits. Reactors produce heat, and you can convert heat to electricity, but you can also use heat to do other things. And so when you factor in, for example, if we look at remote location in Alaska, they need heat and power, so you're getting some benefits where if you levelize over the heat power applications, it becomes more competitive too.
Thank you.
Yes, in the back.
Just one more. This is a little bit more applicable to your last slide, but in total, how many projects does INL have, current and future?
Yeah, so it's a little harder to answer that than you might imagine, because there's reactors at different, or projects at different scale. So, I mean, this timeline lays out the number of projects that we have, that we are actively working on. There are discussions with other developers that Lori mentioned that have interest in demonstrating reactors on the site, but they perhaps aren't at the maturity level that we would note them here. If you look at this slide, you can, I think Lori pointed this out, Marble, Pele, McCree, Aurora are at our site, Voyager at our site. So there's 5 shown here, and there are others that are interested in demonstrating on the site beyond that.
And there's many more that are interested in using our test beds and our testing facilities, so that they can, get materials that will meet the performance of the reactor, and to, the INL can design fuel from beginning to end. We can do all of the irradiation studies and the materials test. We can do that on, for these industries coming in. We're going to be able to provide them potentially some fuel, to start up the reactor. There's all sorts of things they're coming to us for besides demonstration.
Good, very good question.
Thank you. And back over here in the corner, and then we'll move to the next topic.
If the SMRs and microreactors, have proliferation in the market, sort of along the lines of the gentleman's question over here, what will that do to fuel prices and fuel availability?
Yeah, that's a really good question. You're going to have to develop a supply chain to support all that. So I would wager that if there's that strong interest, there's going to be a lot of investment in fuel supply. There's plenty of uranium available domestically and internationally, that's not an issue. We need to develop the supply chain to enrich the material for the fuel, make the fuel. That'll have to be developed to support that scale of infrastructure, for sure. And so it'll sort of work its way along. You know, right now, there's a lot of interest in investing in clean energy, so we have strong signals there will be investments. And then, of course, the government is interested in clean energy as well and making investments.
How we're getting that started.
Yeah, I want to talk about that a little later.
All right, let's move on to our next subject area, and we're talking about engaging with communities. And that's Stephanie Weir's expertise area. Can you tell us a little bit more about yourself, what you do while they're voting on the first question?
Thank you, Joe. And thank you to everyone who came out today. I mean, engaging with communities is, of course, what I'm passionate about and talking about. And so it's wonderful to see all of you here today to spend your time coming out this afternoon. So as Joe mentioned, my name is Stephanie Weir. I joined the National Reactor Innovation Center just about a year ago. So I'm sort of new to the nuclear community. But I'm just really excited to be a part of it. Prior to joining NRIC, that's the National Reactor Innovation Center, it's another one of those acronyms that we throw around, but it's easier to say than National Reactor Innovation Center. So before coming to NRIC, I was an attorney in private practice, and I worked on a lot of environmental cases. And as I worked through those cases, and in particular, there was one case that really struck me. I was involved in a Clean Air Act case, and seeing the different pollutants that come from different industrial and energy generation facilities, and the disparate impacts on the communities around them, really struck me. And I started looking at it deeper and deeper, and realized that, you know, I'd always thought that nuclear was going to be a critical component of having clean air and helping in this facet. And then, as the advanced reactors have been developing, they bring a lot of wonderful attributes, like Jess has already mentioned, to bear on this very important topic. And so when the opportunity came to join NRIC as the Siting Regulatory Strategy Manager, I was really excited and just jumped at the opportunity. So, which question did you get?
Okay, all right, thanks. Well, it's actually a close vote, so maybe we'll handle both. First up is, what are the risks and benefits of having a new nuclear project nearby?
That's a great question. I was hoping we'd get both of those, so I'm really excited about this. So of course, there are always risks and benefits on both sides of any construction or industrial facility. So I like to look at the benefits first. Of course, abundant, clean energy. Energy that can be generated without creating or emitting any criteria air pollutants. So we're talking energy without smoke, smog, and acid rain. It's also having a facility in your neighborhood actually creates an economic benefit for communities. Not only is it high-paying, long-term jobs, but there's secondary benefits from spending and taxes as well. It supports energy security for the community and for the nation. And of course, with advanced nuclear, it's really interesting to think about the flexibility that these different reactors bring to the table. So as we kind of talked about, there's different coolants and there's different technologies. And with each of those comes additional opportunities to use the energy and heat in different ways, not just for electricity. And so the advanced reactors also have some really great benefits that help with safety and security for the reactors and for the communities. And so that helps mitigate some of the risks that everyone always, it associates with having a nuclear facility in their neighborhood. All industrial facilities, all industrial activities have certain amounts of risks. But the nuclear community, the nuclear industrial facilities are some of the safest in our entire nation. They have high standards for safety, security, training. We do a great amount of emergency preparedness, and we work really closely with the Nuclear Regulatory Commission, which is the agency that regulates all nuclear reactors. And they are considered the gold standard for safety across the board for agencies. So did I answer the benefits and risks?
Let's see, well, the next question was how do developers choose where to build a nuclear plant?
So I love this question too. There's a lot of different factors that go into making this kind of decision. Of course, one of the first things a developer would do is look at what are the business cases, what are the potential purposes for building a facility. So they're going to ask themselves questions like, am I putting electricity on the grid, or am I trying to serve a particular industrial customer who wants electricity and heat? Or is it district heating for a remote community who also needs electricity? Or maybe even we're talking about supporting a hydrogen hub. So there's a lot of different applications, and each of those applications will help you understand and target particular regions for further analysis. And so then once you've identified particular regions, you'll want to go and dive a little bit deeper. And so you're going to look at different factors and help you screen in and screen out particular areas within those regions. And one of the really important things in this is, what does the community think about this particular project? I mean, it can make or break a project. And so it's really critical, and it's really top of mind for a lot of these developers. I mean, I'm happy to say that we're actually seeing some of these newer reactor developers out there engaging with their communities already. We've seen that in the community of Cameron, Wyoming, for example. Of course, you have to look at physical considerations, right? You want to avoid wetlands and critical ecological areas, and of course, avoid cultural resources that are sacred to communities. But you may also want to look at what are the assets of that area. So is there access to transmission lines? So do you have good roads? Are there resources like Idaho National Laboratory nearby that can help support your project? And so then, of course, finally, you're going to look at what are the regulatory requirements, and that's federal, state, and local requirements as well.
I'm sorry if I missed it, but you identified the benefits of having it, but I didn't hear a lot about the risks. What are the risks of having it?
Well, it's associated with typical industrial risks, and there are concerns, of course. I mean, people have concerns about the possibility of having a really bad day at a nuclear facility.
What does that mean? What does that mean?
Fair.
I'm not clear on these things, so
Well,
I'm not sure what that means.
I mean, I think we can all bring to mind 3 Mile Island or things of that nature. But that's where these advanced reactors and the lessons we have learned over the years from hundreds of years of operational experience means that, in particular for the advanced reactors, we're looking at no potential off-site impacts from radiation based on the inherent and passive safety features of the reactor designs. So we're mitigating the risks that would be associated with it by the design of the reactor. You know, in a lot of these cases, the reactors are much smaller and much simpler because, and you know, like the more complicated a system is, the harder it is to make sure everything works all the time. We are trying to, the community, the industry is trying to pare it back and have more simple designs, and simpler is easier and a lot more predictable. I don't want to moderate, I'll talk.
Let's go over here.
Just really quick question, you mentioned emergency planning around nuclear reactors close to communities. Are there efforts to shrink nuclear, or the emergency planning zones around advanced and small modular reactors?
So the Nuclear Regulatory Commission is taking this into consideration, and they're working on it. So we anticipate that some of the EPZs, the emergency planning zones, will be significantly smaller. And we're just waiting to see where the NRC finally lands with respect to all of the different designs.
And over here, sir?
I did some research many years ago on treacle fuel, which was advertised at that time as a fuel that could not overheat. Is that accurate to say that?
Yes.
so the fuel is a high temperature fuel. When you look at whether it can overheat, it also depends upon the reactor design, so it isn't just the fuel alone. The benefit to that fuel is it can withstand higher temperatures, so this gives you the ability to operate the reactor at a higher temperature, and also, for example, if you were to have an instant release cooling, that it can tolerate those higher temperatures. If you heat it to the temperature of the sun, it's going to melt, and we do experiments on that. We do irradiations in our reactors. We heat up the fuel, and we find out exactly where that happens, and those become design limits for the fuel, so we know where that happens. Sometimes you see it as melt-down-proof fuel or something like that. I think that's inherently, because we know where those limits are, we design our systems with sufficient margin and contingency that it's impossible to be in that position. So it's a broader answer than just the
Thank you.
I should point out also that several of the microreactors on the list are proposing to use that type of fuel with different types of coolants. And if you had someone over here.
So I guess I'm struggling with one thing here is how we get to completely carbon-free if we look at the whole fuel chain. And now, are we saying that all the uranium you're ever going to need has already been mined? Is that where we're at, or? That might be a lawyer question, yeah, I don't know.
Yeah, and so, the generation at the reactor is carbon-free. The reactors produce no CO2 emissions, they burn nothing. So the question is about the supply chain. What's the carbon in the supply chain? You have to mine uranium, you have to truck uranium. If you look at all energy generation sources, there is no generation source that is, if you look across the whole supply chain, it'll be zero. Obviously, fossil-based definitely produces more because it's produced as part of the energy generation. If you take all the carbon produced in that whole supply chain and divide by the energy produced by that fuel, so it's the carbon per unit generation, nuclear is as lower than renewable sources. Renewable sources have mining and material processing as well that produce carbon. So carbon-free, you've heard up here, tend to say low carbon. The carbon-free power project, the reactor itself is carbon-free if you include again, the full life cycle, as you will. It's incredibly low carbon.
But not carbon-free, right? That would be-
Yeah, the generation is carbon-free. If you look at the whole life cycle cost, and there's data on this. You can Google the International Panel on Climate Change, where it shows that nuclear is half the carbon of solar and wind.
But solar and wind doesn't have to deal with the radioactivity, correct?
They have,
No, I mean, not as much.
yeah, they don't use nuclear fuel, so
Right.
they don't produce, radiated nuclear materials.
Okay.
Very true, yeah, that question came in on the email as well. And so I knew about the life cycle issue, but I looked that up and came up with the IPCC, the study that they did that measured the life cycle costs. And nuclear was, at the top of the list at 11 grams per kilowatt hour. The only one that equaled it was large-scale solar. Or, no, I'm sorry, onshore wind. But we've got some links to that study if you want to look at that. And then our sister laboratory, the National NREL in Colorado, they've done numerous studies on this well, looking at, from cradle to grave, the entire life cycle of all the different energy sources. And they've got a lot of good data on that as well.
Thank you very much.
So when, we often tend to get caught up in saying zero carbon, and we really shouldn't do that if we're talking about life cycle.
Yeah, well, the point is to eliminate carbon emissions and get as low as possible. Nuclear clearly is lower than any other possible sources.
Questions about security, and there's two parts. The first is, the security like the kind, where the Russians are bombing the Ukrainian, or missiles are coming near the Zaporizhia plant. And if we put all our ducks in one reactor, not only do they get cooked, but there's higher risk there. so there's that risk, and then just the risk of one system going down. So, you know, there's the SMRs, et cetera. Can you kind of talk about the risks in terms of both bad actors, foreign actors, as well as just the vulnerability of a power plant that's a nuclear power plant?
Versus a more diversified grid, lots of solar panels and then a little.
I'm sorry, what was the question?
Sorry, I just tried to amplify it.
Versus distributed, I think is what he said.
Right.
Well, I think anytime somebody bombs any kind of industrial facility, you have a lot of dangers in any of those. I think those of us who were around during the Iraq wars and 20 years ago, they were bombing oil fields and there were huge plumes of oil going into the air. So there's always dangers of that, and certainly nobody wants anybody to attack energy facilities or chemical producing facilities for that matter of any type. Those all have hazards. So there is no hazard solution to that. So what was the second part of your question?
Just the distributed versus
Distributed.
facilities that are easily identified.
Right. So I do want to say that our individual large-scale nuclear plants right now in the gigawatt range. So we talked about megawatt range micros, but the gigawatts are obviously 1,000 megawatts. They're very large. They typically have very strong physical security at their sites, and they have containment structures that are very robust to physical attack. So that's one thing. The topic that I'll be talking about in the next section does start talking a little bit more about distributed systems with different types of energy. There's, I think we need to start thinking about an energy paradigm system where we're going to more distributed systems with smaller individual sources. So there's always, there's no such thing as a free lunch if we want energy, right? We're going to have to take risks and manage them for any kind of energy system that we have. Coal, nuclear, wind, whatever.
Yeah, one connection on that, as Stephanie mentioned, nuclear is regulated by the Nuclear Regulatory Commission. They have, in connecting to what Mary Ann said, they have particular requirements on aircraft, impacts on nuclear plants, on security of nuclear plants. So they're regulated quite heavily, and the requirements that the plants are going to have to meet and the microreactors are going to have to meet in order to be approved and operate.
Yes, and actually that was part of a study that was done right after 9/11 when I worked at Idaho National Laboratory on risks of aircraft hitting nuclear power plants. Incredible analysis that was done, and quite a few security requirements which came out of that study that enhanced the safety of the system. And it wasn't just big nuclear plants, it was things like medical facilities using radioisotopes, research reactors. They covered the entire thing. NRC is a very conservative organization. I worked with them very closely for about 6 years back in the first decade of the century, and they are extremely conservative. They do a very good job of making sure that our nuclear power plant system is safe and secure.
When you're talking about the life cycle of different energy sources, and you're looking at nuclear and determining whether it's carbon-free or how much carbon emissions there are, we've talked about mining, and I can understand that every energy source has, you have to get it from somewhere and it takes some kind of an industrial process. But do they take into account in determining the whole cost, what it costs to deal with the nuclear waste, to store it, to remediate it, to recycle it, to monitor it for hundreds or thousands of years? Do they include that?
Yeah, we could go look at the study and look at all those details. And on the back end, the store and all we dispose of the material, there's actually very few carbon emissions. The used fuel from our existing plants are in, concrete, steel storage containers that sit there. They don't generate carbon. The other aspect with nuclear is you produce a lot of energy with a relatively small amount of material. So if you do carbon per unit energy, the amount of material it actually takes to do that for nuclear is much lower than basically any carbon emissions, that you just don't have to mine as much stuff, extract as much stuff like uranium or steel or concrete than other sources. So that is also another reason why it's very low. But the life cycle cost, I'd have to go back and look at the IPD study and their references, what they did, but the intention of all life cycle costs, or life cycle carbon, it's also uses the word cost, but carbon.
We're starting to run a little bit over on time. We're gonna come back to your question if we could.
Yeah.
So I don't wanna leave any of these. I love the discussion going on. We're gonna hit our last couple of poll topics, and then we'll go a little bit more open-ended. So the carbon-free power project, which of course is the NuScale project, and we've already talked quite a little bit about this. Go ahead and do your vote on the question. I just already got to introduce himself, so we won't do that again. All right, we got, we're neck and neck. No, I'm pulling ahead here. It's like a horse race. We just watched it. Okay, I think we got a clear winner. What are the roles of the different companies and public entities?
Let's maybe have Jess give kind of a surface level overview of what the carbon-free power project is.
That's good. That might be, yeah, you might not be familiar with it described that way.
Yeah, so the carbon-free power project is a project being led by the Utah Associated Municipal Power Systems that will deploy a NuScale small modular reactor on the INL site. This reactor, I think I mentioned this, 6 module reactor, 462 megawatts, so it's quite a bit of power. Each megawatt means each module means 77 megawatts, and it'll supply nuclear energy to the region, actually. So I don't know if that covers everything that you had in mind.
Okay. And let's go back and do the second place question, even though the gap is pretty wide. How is it different from other reactors at INL?
Yeah, so our reactors at INL are utilized for research and development. We develop, use our reactors like the advanced test reactor to irradiate nuclear fuels, to test the fuel, to understand how it performs, what the safety limits and things like that I talked about before. We also have a unique reactor that's able to pulse at a very high power level to test these materials. So, but these are from an application point of view, research and development machines. The UAMPS carbon-free power project, NuScale reactors for power generation, for electricity generations, what we would call a commercial reactor, where they're selling a product, electricity.
Okay, and then any follow-up questions there? Yes.
Just, this might be a different direction, but I think it's follow-up. Isn't it true if we kind of go back to the free lunch issue, and ignoring carbon for a second, isn't it true like one home with a couple solar panels on it, if they were everywhere, like you guys are suggesting nuclear plants should be, would one home be a much more pointless target for any foreign bad actor? I mean, looking at scale of production per facility
Well,
you talk about?
I mean, you get into complex scenarios. You have distributed source like that versus a few sources that you defend very well. You get into the concepts of how you defend things.
Yeah.
The other thing you have to look at, you can look at that one scenario, but then you can look at other scenarios such as, what do those homes with solar power do at night? Do they have energy storage? What if you have an extended period with clouds? And so you've got to look at the holistic answer there. Certainly solar panels on homes, probably many of you have on your homes, there's definitely value to that. We would seek to figure out how to integrate energy sources, and we'll maybe get to a question or something on this later on how nuclear fits as part of an energy system. Not just a standalone solution being nuclear necessarily. So I think there are options that you can look at.
Okay, so right over here.
Yeah, small and large are relative terms. Can you give us an idea, that last slide that was showing that reactor, what would you give the size of that module?
We're talking about the new.
Yeah.
Okay, those are 77 megawatts. Those would be, and there's 6 of them. Oh, you mean physical size? They are designed to sit on the back of a tractor trailer, for example. And it may be one of these oversized loads, so it's not. But they're designed to be made in a factory, transported in that way. That's you
designing to be road or even large transportable.
Yeah.
And I think we have one more question over here. Yes.
Would it be dangerous if one of these, transportation trucks were to get in a crash or some sort of vehicle were to crash into it? Would something bad happen from that?
Well, we have a lot of experience with transporting nuclear materials around the country. These types of things are very well protected. They have very, very strong transportation systems available for different types of systems, and it would need to, you're not going to start a chain reaction by hitting them with a truck.
Yeah, I was just curious, like if that were to break, if it were to somehow be bad, if the matter were to get everywhere. I don't know, I'm just curious.
The nuclear parts of the reactor are well protected and very well protected in the transportation system. I'll just say that.
Yeah, if you look at, transportation of spent fuel is a very similar thing. These casks in San Diego or Marianne did enormous testing on dropping these things from high heights, running a train and then running a truck, and they're tested to be extremely strong. There's never been an accident of shipping of spent fuel that's even come close to anything like this. So from the engineering point of view, these are some of the strongest transportation systems that are available, and they're tested. They're physically tested. It's designed and tested to ensure that the types of accidents that would occur would not result in a release.
Thank you.
So, and there's some cool video. If you go on YouTube, you can find some videos of things crashing into these, and they're pretty cool.
And another question over here.
And not to detract from the content, the information you just gave about transportation, it's my understanding that the components of modular reactors are shipped and then put together on site, and no fuel is loaded until it's at the site and it's ready to go. There's nothing that's being shipped, it's just metal and components. They don't have any meaning until they're assembled and then the fuel is loaded at the site. So there is no transportation of anything scary.
Like the NuScale reactor, again, the vessel that you were asking about transportation, that's shipped, there's no fuel in that. The fuel is shipped separately, very similar to we ship fuel for the current reactors. And when done, it'll be moved from the reactor to a cooling pool for a limited period of time, and then into dry cast storage, which is the same system used today. And then at the point that there's a repository, that fuel would then be moved to the repository.
Yeah, I'm glad you pointed that out. There, in the case of the NuScale design, that is not, it's not one that they would ship the fuel in. That would be handled separately. I'd add that all of the transportation casks, if they're allowed to go on public roads, they have to pass all of the Department of Transportation regulations for that kind of thing. And that involves that kind of, accident testing. So anything that's used to transport something that even could represent that kind of a risk. We have to do the due diligence, or the microreactor vendor, has to cover that. And one more question.
Okay. The MIT Sloan School of Business has put out a carbon climate change game that talks about various solutions, and of course nuclear is one of them. And one of the things that they've said is that it could take a very long time to commercialize and deploy, and of course there's been a history of overruns and things taking longer to turn on, and also there are very, very strict requirements which probably play a part in that. So what do you see now in these modern times with these new reactors in terms of deployment times, like from now to when we actually see these operating?
Or maybe, yeah, I'm happy to answer it. It's definitely true when you look at the plants, including the current ones, some of the current ones under construction, they've taken longer than, what was planned. Now, you have to realize those are first of kind plants. First of kind plants there's uncertainty with, and then if you move beyond first of kind, it becomes more certain. In fact, if you look at the history of the first of anything, and it seems to take longer than what we planned. Now, as far as these other plants, the other truth is we've gotten really good at manufacturing things, right? In contrast, manufacturing construction and large-scale construction. The large gigawatt plants, typically when you're building those are the largest construction projects in the state or in some cases in the country. And so they're very complex. You shift to manufacturing where you're doing things in a factory, think of making a car or making a plane, you have a very controlled environment. If you make more of something, you get a lot better at it. And so you will have, the plan is to look at other industries that do more manufacturing-based products, and that nuclear will be able to achieve schedules and quicker deployment schedules because of that. So that's the change in technology benefits of going smaller than larger, of moving the needle from construction to manufacturing.
And we're seeing the supply chain come along with that idea as well, right, Jess? I mean, they're looking at modular building manufacturing where they can build a building like this size modularly in a factory and then bring it in and assemble it around the nuclear vessel area.
Stephanie might want to talk about this. We're learning, we're looking at other industries that have also improved construction technologies. And so there are a few that Enric is working on that could really also improve the reliability of scheduling and reducing cancer.
Yeah, so Enric was really stood up to help accelerate the development and deployment of these types of advanced reactors. And so we're doing that in a lot of different ways. One of the ways is the test beds and providing facilities for people to come in and test on an accelerated path. But hitting on this construction topic, we have what's called the Advanced Construction Technology Initiative. And what we're looking at is we're looking at taking best practices from other industries, aerospace industries, so they use digital engineering and digital twin technology to accelerate the development and design process. But we're also looking at using vertical shaft boring technology, so the types of technology that they use to core for tunnels, to improve the time and minimize the amount of earthwork that has to be done. We're also working on demonstrating what's called steel brick technology, which is a modularized steel and concrete approach to construction. And these are all technologies that have been used in other industries to very great success. They just haven't been demonstrated for the nuclear community. And so by doing this demonstration project, and we're going to build a facility, a scaled facility, using these technologies. And we're bringing the Nuclear Regulatory Commission in to oversee some of this so that they can just observe how the process goes and get very comfortable with these technologies from other industries so that they can then be brought to bear on nuclear build construction. And most of the overruns on the current fleet are steel and concrete and construction. It's not delays related to the nuclear technology itself.
Okay, then one more question over here.
Yeah, I'm curious, how much of the slowdown in adapting this technology is in the regulations around building it on land? And would you be able to bring it to market more quickly if, say, you did it in international waters and that created along a power line to shore?
There's definitely people looking at that, and then combined with that is actually putting reactors on barges that you make in the same in ship builders, right? They're good at building large things out of steel, and there's definitely interest in that. I don't know if the international waters part buys it. That almost may sound like a workaround. Somebody, it's definitely going to have to be. As we talked about the regulatory process, somebody has to own that process. And I'm not an expert in international law and how that works. And maybe it would work, but certainly a different way to deploy would be on barge. You can move it around. You can use ship constructors to make it, and there could be some advantages. We build very large ships very effectively these days.
Well, I mean, a lot of people who have these things
It's, well, yeah, it's an interesting idea, but just saying, I think that is
You know,
really important.
there are definitely interested in looking at those things. I don't know the answer if there's a benefit, and, you know, maybe somebody else here can comment on it, but there's definitely people looking at these as alternative concepts.
So I will just chime in a little on this. So NREC actually has a maritime nuclear applications group that we're supporting and we're participating in. And we are working with both the maritime community as well as nuclear community to bring these two groups together so that they can develop relationships and explore potential opportunities for maritime applications of nuclear. I will say that one of the reports that we're working on right now is an analysis of the regulatory framework that would be applicable to this, and it's a lot more complicated than you think. We're working on it, and there are actually a lot of different potential applications for nuclear in the maritime space.
Yeah.
Would those microreactors be powerful enough to power a cargo ship if you wanted to retrofit it just for transportation purposes?
Well, that's a complicated question, actually. And so maritime nuclear propulsion is a very sensitive subject. And so we're looking more at different applications of nuclear. So generating power to provide hydrogen or other applications. But eventually, we do think that nuclear will be a solution for decarbonizing the maritime space.
I can definitely say that is being looked at more and more. You know, our nuclear navy is, you know, the best example of that. You know, a ship the size of an aircraft carrier, you know, the Gerald Ford that just launched a couple of years ago was powered by two essentially small modular reactors. It's an extremely powerful, compact design that is probably not ideal for a power plant, but it works great for a propulsion system for a ship that size. So, you know, applying that to getting rid of all the fuel burning that the cargo ship fleets going back and forth across the oceans, how much carbon that generates. You know, that's very much on people's minds right now. You know, is it going to be worth it to look at commercial shipping, you know, nuclear again? They looked at it a long time ago in the 60s. We've got one more cold topic to cover, or at least one. We got one or two? Just one, okay. Let's do this last one and then we'll get back into the open forum here. And the topic is Marianne's, and it's beyond electricity. And by beyond electricity, we mean what other applications are there for nuclear beyond just generating electricity?
Right, so this has been touched on in several of the previous comments. How can we harness the fact that nuclear plants produce heat, right? So many of our electricity generation technologies that we use today, some of them produce only electricity, such as wind and solar, but many of them produce heat, such as burning coal. That's a heat, and then you put it into a steam generator and you spin the turbine and create electricity. That's the way nuclear power works these days. But how could we also use nuclear in an area when we're trying to incorporate renewables into a complex grid? They're not baseload power sources, they're intermittent. Nuclear can be baseload. We can make it more load following than it currently has been. But how can we take all of these different types of sources, as you can see on this slide, of electricity and heat, put them together with storage. Storage is the holy grail, of course, here. We need to have efficient grid-scale storage along with these different types of power sources and use them for the entire spectrum of different applications that you can see along the bottom of the slide. Electricity, but also heat for chemical processes, to desalinate water, to create hydrogen. Of course, hydrogen is also a potential energy storage mechanism. Power industrial processes, all do this all in an integrated energy system. We have quite an organization and a collection of efforts at INL going on right now on how to do that, both from a modeling and simulation perspective, how you get it into the grid, what's the right types of things you can do in order to integrate these systems together to really create a new type of paradigm for energy in the future. And hydrogen production is a big part of that, and we are part of that at INL. We're focusing on high temperature electrolysis. We were talking about carbon-free before. Hydrogen mostly right now is made from natural gas reforming, so it's made from a carbon source. But you can make hydrogen by splitting water electrolysis. You can do that at either low temperature or high temperature. Low temperature electrolysis is easier, but it's less efficient. High temperature electrolysis is an area that's really ripe for using nuclear heat to create the higher temperatures. You need to have higher efficiencies to create hydrogen, which you can then use for fuel cells. You can use it to make ammonia. You could potentially use it for grid scale storage as well. So there's a large interest in our laboratory, and I think nationwide, in terms of how we can create these integrated energy systems for the future, which will make better use of all of our different types of energy sources, and then how we can best use nuclear within that system as a hydrogen producer, but also other applications as well.
Okay, any questions on this topic? Yes.
Yeah, so they said, what's nuclear hydrogen? Well, I hope I explained that a little bit, that basically it's making hydrogen used by splitting water using nuclear heat to do that.
Yeah, you covered pretty well, I think. But what was your question over here?
I was just curious, so if uranium mining, processing, and, construction of the power plant, transportation of the waste, and transportation in general all use all use carbon emissions, how would this be the solution to that problem?
If you have a solution to the problem, how to do mining without creating any carbon and any kind of transportation, we're wide open to listen to that. I think if you're comparing, are we going to be able to get rid of 100% of carbon emissions in our society? I don't think that's likely. And in fact, right now, if you look at the percentage of energy that we produce nationally from fossil fuels, it's close to 80%, so we've got a long way to go. So we're looking for any way that we can reduce those carbon emissions, and as was pointed out earlier, you need to, if you're going to be producing wind turbines, you have manufacturing processes, you need raw materials to do that, you're going to have to transport. You've seen those wind turbines on the road, right? They're huge, and they're very difficult to transport. So we've got similar problems for many of our technologies. And as Jess said earlier, that there have been comparative studies done among different technologies, and nuclear is, he said, I haven't seen that study, I should probably look at it, that it is the lowest life cycle carbon cost. But it's not zero, right? It's zero when you're actually making electricity out of, or making, splitting the atoms, and it produces the heat and makes the electricity.
Okay, let's go over to the other side of the room now.
So two things that are kind of related, I'm tracking as best I can. One, this should be really easy. Just generally speaking, how is the NRC on NuScale right now as far as, how much are they on your assets?
Well, I don't know if we'll talk about this. So NuScale went through the process of licensing process. They're doing a two-step process, went through their design certification process. That was just signed off on for their 50 megawatt version. NuScale will be submitting for their 77 megawatt version and updating that design, because obviously 77 megawatts is more energy than 50 megawatts and produces more energy. So they have a design certification. Now, in order for example, the UAMPS reactor, in order for that reactor to be approved, they'll also have to go through the second part of that, which is the construction operating license. And so NuScale, or UAMPS, is planning to submit that, I believe, in a year from now, roughly a year from now. And so the NRC will review that construction operating license, and upon approval, they'll build a reactor.
So just NuScale's been doing this for 20 plus years, right? They started applying and working toward their license 20 years ago.
So somebody's reading fine print, I guess, is the question, right?
Yeah, the design certification underwent, I think it was like a 40-month review, so it's a pretty long period of time.
What was your other question?
My other one is a little more complex, and I invite anybody to shoot at it. It's just how do we solve the weapons proliferation issue, which is really this industry's legacy, while we're chasing
on the proliferation area, it actually isn't a legacy for civilian nuclear power. Fuels used for, thank you. The fuels used for civilian nuclear power is low enriched uranium, high enriched uranium. So I don't believe that's actually a factual statement. There are strict, when it comes to non-proliferation security, the reason we talked about security and safeguards, we have the internet, in addition to the NRC, there's also the International Atomic Energy Agency that performs safeguards, so there's a lot of attention on this and this technology. So that's my answer to that.
Yes, sir. Sure.
I'd like to follow up on the question that Lisa asked earlier about scaling. Jess, I think you suggested that in the 70s we were building dozens per year, so 10, 20 gigawatts a year, something like that. Right now, 20% of our electricity comes from that nuclear base. Mary Ann pointed out that 80% of energy is fossil fuel. Can you scale, not you, can this industry scale adequately to move the needle by 2040?
And I think there'll be other answers to this. If you're looking to say we're going to totally replace all energy generation with nuclear, that's probably not very reasonable. Certainly, if you look at these demonstrations time frame and moving to deployment, you will be on your path. 2040, 2040 date, and maybe talk about why you chose that date. We have a goal, the administration has a goal for carbon zero, net zero electricity generation. Let's see, I'm trying to think if I have that right.
I think it's 2050.
2050. And it's going to take a lot of sources to get there. So nuclear will play a part. It can build, we have to develop, the question up here is a really good one, the supply chains to support that has to be developed. These reactors, factory fabricated, can move much more quickly. If you look at good examples, look at France. They converted in the 70s from carbon-based to nuclear, primarily from an energy security point of view after the oil embargoes, and they went from zero nuclear to 75% plus in a decade. So you have to follow up.
Well, that's electricity generation. If we're going to decarbonize, we need to deal with the energy consumed economy-wide, not just electricity generation.
Sure.
So
Right, so we have to do
is it
something about
possible
the
to make up?
fuels, right?
But is it possible to have 100 gigawatts of new installations per year at the end of the 2 decades? Mark Jacobson from Stanford writes off nuclear because he said you can't get it fast enough to fix the problem. That's why I picked 40.
Okay. Yeah, 100 gigawatts a year is a lot of power. I don't know any technology that's going to be able to do that. Maybe I'm wrong on that.
Oil.
Okay. Yeah, so maybe, so maybe carbon capture. There's definitely looks at that technology as well. That's why I think to achieve that, you've got to look at multiple sources, renewables, carbon capture, net zero. There's also work looking at not only carbon capture at the energy generation, but are we going to be pulling carbon out of the air? It takes a lot of energy to do that. I don't know, but in a realistic scenario, you look at the different scenarios, I don't think there's any one technology that's going to get you there.
You mentioned France. One of the things I looked at in France is if they established a common design and they cloned it. So their costs are way lower than a lot of folks. And I'm assuming that the NuScale program is aiming at that.
Yeah, and each of those modules are the same, 77 megawatt modules, factory fabricated. And since they're smaller, you're going to make more of them, and the idea is to get better at making them. It is the case, there are a lot of different concepts being looked at. Those are going to have to be worked out, which are the best, which are the most cost effective. We live, in the U.S., there isn't somebody picking and choosing the winners. We're giving everybody an opportunity, and let's see what develops out of that. So it's not the same type of environment that France had. And by the way, France chose American technology, Westinghouse technology, and ran with the best technology available at the time.
Yes, here, in front.
So we talked a little bit about maritime applications, and I'm wondering, you know, thermodynamics says you're going to lose some efficiency converting nuclear into hydrogen. Would we be, and these ships use megawatts and incredible amounts of energy, and, you know, they're going across the ocean from Asia to here, you know. If you want to buy some underwear, they're made in Thailand, and they've got to go across the ocean. So my question is, are we better off using some form of very small modular reactor in these ships, or are we better off with the hydrogen hub that, you know, that's being formed along the west coast, for example?
Well, I think that I think we're really exploring all of those options. And I do think that in time, we will see nuclear propulsion for commercial civilian fleets. I do think that's eventually going to happen. The question is, what does the timeline look like?
Well, and it's also what's the right way to do it. In other words, what dictates when you're going to use nuclear for that and when you're going to use a hydrogen hub? There are different considerations.
Well, and that's actually one of the things that we're looking at in some of our research that we're working in the Maritime Nuclear Applications Group. They're working on analyzing the various use cases and trying to identify the technology that's most appropriate for the different use cases. And so I just want to kind of go back to the question about having a singular design for our reactors. One of the things that I personally think is really fascinating about the time that we're in right now is that we have a lot of different reactor designs out there, but that gives us a lot of flexibility and opportunity to use the right reactor design for the right application. So it's not a one-size-fits-all, right? The needs that a community may have in rural Alaska or remote Alaskan communities is going to be different than a mining facility in the continental United States, as opposed to a ship, or to these various different applications. But by having these different technologies that have their own strengths and make them perfect for a particular application, I think that's one of the really fascinating things about our time right now.
And back over here.
Sure, so just, hopefully this might just scare us a little bit. What, if anything, does the INL currently do to advocate for consumer efficiency and to lower per capita usage? In other words, if you want a bigger piece of the pie, make a smaller pie, right? Is that part of your guys' advocacy, or could it be?
Well, I know as a national laboratory, we do technical work for the Department of Energy. We're not a lobbying organization. In fact, we're not allowed to lobby from a legal perspective. What we can do is provide technical information to various people like yourselves, but also people in the government. And we can tell them what we think are good technical solutions. Certainly energy efficiency is really important for everyone as we move forward. We would always advocate for people to use energy efficient solutions for transportation, manufacturing, and everything, but we aren't allowed to go out there and say, INL says you should use less energy. That's not our role in the world.
Yes, and right over here.
Yes, and first, thank you so much for creating this opportunity to have a dialogue. We really appreciate your driving out here and creating this. Could you,
Thank you.
could you perhaps provide kind of a quick check of, from a global context, thank you so much. I have a much better perspective of where INL's at, but in terms of where we are as a country relative to where other countries are in the commercial deployment of SMRs and microreactors, particularly Canada, and just other comments, kind of from a global perspective of where we are.
Okay, maybe I can start with that. First, to realize, the United States generates more power from nuclear than any other country. China is rapidly increasing. They're deploying a lot of light water reactors, same technology that we have. In fact, they deploy Western developed reactors in their country. So we're a leader, even though we haven't built any new reactors. We're a leader there. To look at the forward-looking on the advanced reactors, we're also probably a large number or a large fraction of the concepts being developed are being developed in the U.S. some existing light water reactors being deployed there, but there's a lot of engagement by the Department of Energy within Europe, and there's a lot of interest there in small modular reactors as well. There's been some recent agreements signed. Poland, for example, is going to be deploying some Westinghouse reactors. They're largely, almost all their electricity is produced by coal. So they have a significant energy transition there. There's engagements with Romania. There's a whole list of countries, and a lot of those countries are interested in U.S. technologies. There's also, maybe I'll just add to this, the global leadership in nuclear energy, if you look historically, has been, Russia and China, and the U.S., over the last couple decades, despite the comment that the French reactors are all U.S. technologies, the Korean reactors are all U.S. technologies. The U.S. now, because of the work being done, has options to Russia and China, which may not be the best partners. Without going, I don't need to say more there.
Do you have a question for you?
Sure. With the scope of innovation happening in the next decade or two, particularly with work at INL on the SMRs, is there an anticipation of the regulatory structure at NRC adapting in any way? Very much a hugely complicated rulemaking procedure and everything that could go forward. Do we anticipate that changing previously, or is that adaptable to this new technology?
Well, so they are working on it. There is a rulemaking that's underway right now for a technology-inclusive, risk-informed approach to regulating reactors with less focus on one particular technology and being able to regulate a variety of different types of reactors. The the NRC, the commission, has indicated to the staff that they want them to move quickly on this. So they are working very hard on this. There's a lot of information on the NRC website about Part 53 and its development. They're also looking at ways to work within Part 50 and Part 52 of the regulations, the NRC regulations. What's also interesting is that there is a memorandum of understanding between the Department of Energy and the NRC, where they are working together to help each agency learn and benefit from the work that the other agencies are doing. And so one example of how we're doing that right now is that NRIC hosts 2 NRC staff members on rotation with NRIC. So they're working with our projects and they're working with our teams. In fact, the Advanced Construction Technology Initiative that I mentioned earlier, we have a senior engineer from the NRC working on that project. And it's been really informative because he can come in and say, he's not speaking for the NRC, but he's learning from the project, and he's also providing input to, the NRC is going to want to see this. The NRC is going to want to understand this better. And then it's a way of cross-pollinating because through him, we provide presentations to the NRC and vice versa. They come and do presentations with us. So I think that there's a lot of work in this space, and I think that the processes are moving in the right direction to facilitate safe, reliable, and predictable regulation of these different reactor types.
To that end, is there any goal for a timeline on new type certification out of NRC? Or is it, looking at this, there's a half dozen or so types that could be commercially viable. Is there a timeline from NRC application to approval that they're looking for?
They're constantly working to improve their timelines. And so as the reactor developers work with the NRC to develop their strategy for regulation, they'll be working with the NRC to identify what's an appropriate review timeframe.
Yeah, I think we're probably going to do like a couple more questions, and then we'll probably round it out tonight. We're up to close to 90 minutes, I think, right here in the middle.
This kind of covers a lot of this, and that is, obviously we're all feeling urgency for figuring out the carbon situation in the world. It seems to me that the French model is pretty good. Let's pick a technology, the NRC or whatever, and say, okay, this is what we're going to build. And we're going to build a lot of them. That's the only way I could ever see that we'd ever get to this 2050 target.
Yeah, I mean, I think it's a valid perspective given on history. history, one of the questions is actually who picks, right? So in France, the government said, we're picking this one. I'm not sure in the United States if we really want the government picking that technology. Certainly, the utilities that deploy the reactors are going to, they're going to decide on technology, and they may very well say, we've chosen this one technology, and we're going to deploy 20 of them, and try to get a bulk deal on the purchase of 20 reactors or something like that. So you can see some variations.
Yeah, and over here, I think you haven't had a chance to ask
In
yet.
France, when they bake pies, they use the scraps from the crust to make dumplings, spent fuels. In the U.S., we take that scrap dough and put it in dry casks for an indefinite amount of years. What is the deal? Why are we so bad at reprocessing fuel in the U.S., and what needs to change?
Yeah, first comment, since you mentioned France and pie, there's a saying that the U.S. has one type of cheese and many types of reactors. France has many types of cheese and one type of reactor. So good food analogy for France. We actually, when it comes to recycling, we do a lot of research. We're actually recycling fuel right now. I don't know if I would say we were bad at it. What I would say is that we've never reached maturity in deployment of that technology. And so, I think that's sort of the same thing. You build one of anything, you're probably not going to be very good at it. But you're also, the research is also of different technologies in recycling fuel, advantages to whether it's aqueous chemistry or it's it's electrochemical processes, which is what we do research on to improve the economics. And also the scale of the plants. If you look at some of the current recycling plants, are pretty large scale plants, and so if you build one of these at a large scale, it's challenges. So it's all going to hinge on the research and to drive costs down and to be able to efficiently operate the plant. Right now, there's not a high demand for that. We're really focused on getting the reactors up and running. We actually have uranium. We can, the used fuel can be stored, and that's a resource that we can at a later date decide if we're going to recover the valuable materials, or we decide we don't need them. Maybe nuclear didn't take off the way we all planned it to be, or there's plenty of uranium. We're pursuing other materials like thorium. So,
It doesn't go bad like dough, so
yeah,
probably safe.
that's a good point too.
I think one thing to keep in mind is the developers we're working with, they're going to demonstrate more than likely in the United States or Canada, but they are out selling around the world. So picking one isn't really our job. Picking the right technology isn't the government's job necessarily, but the market and the developers, they're out there selling. Their investors are out there selling. They're looking all over the world to place their reactors. And so the United States maintains leadership that way because the NRC will provide the license, and then they'll be able to deploy around the world safe reactors, right? And we're going to have that capability to enable our developers to do that. And we really feel like that is a sort of the goal of what we're doing, is to make sure that these developers, these companies, these investors have that opportunity to go all over.
Okay, let's do one last one, and then we're going to do a couple of the write-in questions that were emailed in.
I'm just curious, I'd like to hear from the group, to what degree do you think we're constrained from the human resource side in terms of the technical skills we need to reach our goals?
We talk about workforce all the time, all the time. As a matter of fact, we were today at a meeting of the State Leadership in Nuclear Energy Commission. It's called the Line Commission. It's an official group of the state of Idaho, and much of the discussion was around workforce. And the workforce that we will need to do nuclear at a large scale will include a large variety of different types of skills. Construction, obviously, for new plants, crafts, technicians, all the way up through PhD researchers. So it's a big topic for us.
Thank you. And then I'm gonna, before we lose too many more people, I see a lot of people starting to drift out. So we're gonna start to wrap this up. Let's do our, you know, our final word cloud and see if it looks any different as a result of the discussion. I'd really like to thank everyone for coming and for providing their input, given these tough questions. I think the panelists have done a pretty good job. If you can give them a round of applause. I'm going to hang around. The panelists might be able to hang around for a few minutes if you have any questions that you feel that we've missed. But let me do just a couple of the writing questions. Most of them I think we covered in the course of what you guys were all asking here in person, but I'm just going to throw this one out there that was written in. Where will you get the HALEU? A lot of the microreactors are proposing to use, it's a new another acronym, I'm sorry, high assay, low enriched uranium. Where is it coming from for this initial load?
I can take that. Eventually, the HALEU fuel we'll need to be acquired through enriching naturally occurring uranium. First, we are trying at INL to provide some initial feedstocks from reprocessing fuel. We mentioned reprocessing before, spent fuel from the EBR-2 reactor, which was operated until the mid-1990s on the INL site, and we have been storing the fuel ever since. So it is now being going through a refining process to extract the uranium, and then they have to downblend it to 20. HALEU is less than 20% uranium. So we talked earlier about low enriched uranium. It's still low enrichment. It's not considered to be a proliferation risk. That's what the definition is, 20%. So it's below that, but it has a higher enrichment value that will be used in the fuels for these new micro reactors. And so we are trying to help. But there is definitely, and we talked about again at the Line Commission today, we had a discussion about HALEU as well, and the whole supply chain for it, and how we need to keep jump-starting the production so that we can have enough for the new reactors.
All right, very good. I also want to point out we have a little survey spread out on all of the tables. Love to get your input. The topic for tonight was set by the people who attended our last panel discussion like this, our last roundup on the 3 Mile Island mini-series that Netflix put out. So we're always, trying to be more and more, respond to the public's concerns and questions about nuclear energy, and that's what drives, that'll drive our topic selection for next time around. So if you have any other questions, feel free to come on up, and I really thank you for coming. We still got some snacks and drinks over here, and some swag over here on the table if you like. And thanks again for coming.
Hey, I don't mean to put you on.
No, that's why I'm here.
I think it's categorized into photovoltaic, solar, concentrated.